Okay, so shall I start? Yes, good, good. Okay, so yeah, so we have started the lecture on equational state, but today I would like to just make a pause on that subject and address the question of neutron stars and how we could describe them, the global properties of neutron stars by solving the general relativistic equations. Okay, and that will also be the subject of this afternoon hand-on session, for which we will solve together the TOV equations and have a list of exercises and questions that you may address during this afternoon session. But in order to introduce this afternoon session, I would like just to make a pause on the lecture on the equation of state and go on the second lecture. And tomorrow we will continue the first lecture. We'll finalize the first lecture. Okay, so so the question somehow is why. So we are all. I mean, we are not really astrophysicists. We are doing nuclear physics or hadron physics. And the question is, why are we interested in stars, in compact stars? Okay, so you know that so let me address this question in this first with this first slide. So you know, so maybe I will do like Pierre. Yes. Okay, so so here, yes, it works. Good. So so the equilibrium of a star depends on the equilibrium between two interactions. So there is the gravity, which tends to compress star. And if gravity was alone, I mean, stars would all become black hole because there would be no interaction, no force, no resistance to the gravity. Okay, so you need something that counterbalances gravity in order to have a stable star. So you need a kind of internal pressure. So in the case of the sun, this is the internal pressure which originates from the nuclear reactions, nuclear synthesis, which occurs in the center of the star and which produce a lot of energy. And this energy tends to go out. And then there is an average force, which is radial and counterbalancing the gravity. Okay, and the differences between all the stars that we see in the universe is only due not to the gravity, because the gravity is universal and it is the same interaction for all stars, but it is only due to this internal pressure. And the equilibrium of a star, so the radius of a star, so the radius translates the equilibrium of the star, changes only because this internal pressure changes. So this is the only thing which makes a difference between the stars. Okay, so for instance, so on this picture you have the sun. Okay, you can recognize the hot spots there, and on this picture you have more neutron star. Gravity is the same between these two objects, and the only reason why one is much smaller in radius than the other is due to the equational state of matter, okay, which is different from the sun. So we have seen last time that the sun is ruled by Boltzmann distribution. So it's a classical distribution. The pressure is density times the temperature. While neutron stars are quantum objects, and you need to describe them, as we have started to see in the last lecture, according to the Fermi distribution, which is of quantum origin. Okay, so let's assume, for instance, let's make a very toy model and a very simple picture of what is a neutron star. And of course, it is what I say is not correct, but this is just a toy model. So let's assume that in a neutron star, I have a uniform density. Okay, so the density there is just flat. And it goes flat up to the radius, and at the radius, it falls. Okay, and then if you have a single density in the star, so you have also a constant pressure, because the pressure is a function of the density for a Fermi gas, as we have seen during the first lecture. So the pressure is just constant uniform until it reaches the radius, and since density falls down, then the pressure falls down. Okay. So in a way, the measurement of the radius of a neutron star gives an information about the pressure. Okay, so if you have a larger pressure in a neutron star, it means that you need more gravity, or it means that somehow in order to compensate the gravity, you can go to larger radii, and therefore a larger pressure means a larger radius of a neutron star, and a smaller pressure means a smaller radius. So you can see now that when we just measure the radius of a neutron star, what we have access within this toy model, so you will see later on that reality is more complex, but with this simple model, we are just measuring the pressure inside the neutron star. Okay, so the radius give an idea of the pressure. But then at the beginning, I said, well, we are interested in the equation of state. So it's not only the pressure, it is a pressure for a given density. And in this simple model, if you want to have the density, you have the radius. If you have the mass, which is also a global property, then you can determine what is the density of a neutron star. It is just the mass divided by the volume of the star. If you suppose that the density is uniform, then this is how you will determine the density. So by knowing the mass and the radius of a neutron star, you can determine what is the pressure and the density of a neutron star. Okay, so, and this is exactly what is an equation of state. The equation of state is the relation between the pressure and the density. So with this very simple toy model, you can understand quickly why since we are interested in the properties of dense matter as nuclear physicists and hadron physicists, we could also access the same information by astrophysical observations of mass and radii of neutron stars. Okay, so this is what this is a program. So the scientific program of this study, which is to obtain some complementary information about the equation of state by adding on top of laboratory experiments like heavy ion collisions. We briefly mentioned it last time, and we'll discuss a bit more for the next lecture. And also Giuseppe Verde, who is here, will give a seminar this afternoon, I think. Yeah. So we want to have complementary information, and this complementary information on the equation of state can be provided by the observation of mass and radii of neutron stars. Okay, so this is the very simple idea which is behind that. Yes. Yeah. Yes. So I do not mention anything about general relativity. This is your question, or? Yeah, you suppress the mass. Okay, so the number density is just 1 over the volume. Okay, so the number density we spoke is in Fermi cube, in cubic Fermi, and this is just a volume. So it counts the number of particles per unit volume. But now, and this is a number density. So now, as you say, I speak about a mass density, and therefore it is a mass over the volume. But in addition to that, I mean, there are also general relativity corrections that we will address later on. It is a very simple Newtonian toy model, uniform density. I mean, nothing very complicated in this model. Okay. So the TOV equations is the modern way to address the complexity of this question. Okay, so let's continue on. I mean, first, let's start with a Newtonian description of star that you could apply, for instance, to describe the sun. So all stars are spherical, so assuming a spherical symmetry is a good way to start. And this is what, so the picture which is here is somehow the picture of a star. Okay, so you have the center. It's not okay. So you have the center. You have okay, the coordinate, so the radial coordinate of a star. And you can say, well, for instance, I measure the included mass, m of r, which will tell me the amount of mass inside this volume. Okay, and for instance, how I can do that? So I just have to integrate from 0 to r. Yes. Mass density. Yes, it's a mass density. Yes. So yeah, you are right. So it should be, yeah, if I want to be consistent with my notation, it should be a rho. Yes, exactly. Yes, sorry. There is a, yes. Can I correct it? Maybe, okay. So if I multiply by, let me see, by the mass of the neutrons, for instance, or the nucleon, let's say, then this will be the included mass, because n is 1 over the volume. No, but this is Newtonian. This is Newtonian. Okay, so we start with Newtonian. Exactly. Yes, exactly. So I just want to anchor the lecture on something that is well known before we. Yeah. Okay. Okay. So the concept of included mass is pretty simple. It is just the amount of mass that you have below a given radius. And when you span the radial coordinate from 0 to the radius of the star, so you go from included mass, which is 0 in the center, okay, because the volume is 0, to a mass at the radius, which is a mass of the star. And then you can convert this integral into a differential equation, which is this one, okay? That tells you that a unit mass, dm of r, is proportional to the mass density. So excuse me, this is a rho times unit volume. Okay, and the unit volume is this, for instance. And I can zoom in what I consider as a unit volume in this system, and this is what I have. So, for instance, let me choose a cylindrical symmetry for the purpose of this demonstration. And so the volume of this system is just the surface, which is here, times the width of my cylinder. Okay, so it is S times dr. And this unit volume is surrounded by pressure. Okay, so on the you remember the strength is the pressure times the surface. Okay, so it is compressed by some strength which is distributed all around. So since it is a spherical symmetry there, okay, so you have a compensation 2 by 2 of the forces. So in a way, and I described hydrostatic, so I don't really care about everything that compensate. But the two forces which do not compensate exactly is the one which is from the bottom and the one which is from the top, because it doesn't originate from the same position. Okay, one is at R and the other is at R plus dr. So so these are the external force, but my small volume has a weight, and this weight is in the gravitational field, and I can express it in Newtonian physics as this quantity G of R, and this is related to the gravity constant times the mass over the radial coordinate to the square. So I can apply, I suppose that I am in a Galilean frame, and I apply the laws of the Newtonian laws, so the sum of all the forces. And of course, I have, okay, I already mentioned I have lateral forces, but they compensate each other. So I will assume that I don't include them. So the sum of all the forces are, so this, the weight of my volume. Okay, so this is dm, which is my unit mass, times this gravitational acceleration. So this is a force, and the force is directed to the bottom. So I put a minus sign. Okay, and then I have the force due to the pressure at R. Okay, and the force is just the pressure times the surface. This is something that we have used already before. And then you have the pressure or the force from the top, which is there. It is towards bottom, so there is a minus sign, and it is a force which reflects what is the value of the pressure, not at R, but at R plus dr. Okay, so so from that, I can say that, for instance, that dm J of R. Okay, so and the, since I'm in hydrostatic equilibrium, the sum of all these forces is 0. Okay, so this is the equation I have to solve. So I can say that dm J is minus P of R minus P of R plus dr times S. Okay, and P of R plus dr, I just make a Taylor expansion. So this is P of R plus dP dr. Okay, so then what I obtain here, yeah, okay, so P of R minus P of R. No, so excuse me, I put a minus here. Sorry, it is a plus. And at the end of so what I have is a minus dP over dr s. Okay, and drs is my unit volume, dV, and dm is written above. So let me use rho of R dV. Okay, so again, I have dV here. Okay, so what I obtain, excuse me. I hope it is clear. So what I obtain is at the end an equation that it's a differential equation for the pressure. So the gradient of the pressure is negative. There is because of this minus sign here. Okay, so it is proportional to the density. Yeah, the mass density. Yeah. Yes, exactly. Yes, correct. Yeah. This is all the n in this slide. Excuse me, I will correct it. Are mass density. Okay, so you see in Newtonian physics, I have to, if I want to describe the hydrostatic equilibrium of a star, like the sun, for instance, I have to solve two equations. So the one related to the included mass, and the one that characterize the pressure profile. Okay, and the pressure profile, if you go from the center to the radius of the star, because of the minus sign, you see that the pressure is decreasing. Okay, and this is also something that we expect, that the pressure starts at a finite value and decreases to 0 when it reaches the radius. Okay, everything clear? I guess this is just some simple things. And as you see, we have two equations, but in fact, we have three variables. So the pressure, the mass density, and the mass of the system. So there is one equation which is missing there. So these two equations just reflects gravity. And the one that is missing is important piece, which is the equation of state. Okay, so the one which have to be added is the equation of state. So how the pressure goes with the density, with the mass density. Okay, so this is what if you want to describe the sun, for instance, these are the equations that you should solve. Yes. Yes, correct, yes. So in fact, so you could apply that to all stars which are but black holes and neutron stars, okay? Because these two objects are ruled by general relativity, and then you have to correct these equations to include this general relativity. But what we'll see later on is that the general relativity are corrections to this equation. So if you understand the origin and the nature of these equations, you can easily understand the general relativity corrections. So you could also describe the equations in terms of the gravity field per unit volume, which is phi. Okay, there. And since it generates a force, okay, you know that this gravity potential per unit volume, if you just take the gradient of that, you have minus the force. Okay, so this is this thing, and the gravity force, as you remember, okay, it is a product of the mass. So it is a force that exerts on this unit volume. So I take the mass, the included mass inside for coordinate r times my unit mass, dm, and it is a force, so it goes like 1 over r square, and it is directed toward the center. So there is this minus sign here. And from that, so you have another equation, which is the fact that d phi over dr is equal to g included mass m of r over r squared. Okay, and since on the previous slide we showed that, then we can replace gm over r squared, which is here, simply by this differential equation for the gravitational field, for the gravitational potential. Okay, so this is how you would do if you add the gravitational potential. Now, if you want to solve it, so you solve it from the center of the star towards the radius, okay, and you can use either Euler techniques or Runge-Kutta techniques, and you have to define the initial conditions. So, for instance, the included mass at the center is 0 because of 0 volume. The pressure is not 0. The pressure is given by you. For instance, you say, well, I want to generate a star with a given value for the internal pressure. Okay, so you can call it PC, and this is what you define in the center, at the center of the star. And then you can solve this differential equation from the center towards the point. So you don't know where is the radius, but you can characterize the radius because this is the point, this is a coordinate for which the pressure is 0. And you know that the pressure, it starts with PC, and then it decreases. So there is, you know that there is suddenly, since it is a decreasing function, there is a point where the pressure passes by 0. And this point is defined as a radius. And if you know the included mass and you know the radius, you know the mass of the star because it is defined as a mass as the included mass for r equal capital R, the radius of the star. Okay, so that's the general principle, and you will see that when we do general relativity, we apply the same principle. So if you understand it there, then you will understand it for the general relativity. Any questions? No, it's clear. Okay, so so here I have just listed several stars, okay, from the sun to neutron stars and black holes. So the three first one are just Newtonian stars, so the stars that you could describe by applying the very simple equations I gave in the previous slide, and the two last are relativistic stars because they require the general relativity to be accurately described. So on the first column, I give the mass in unit of the solar mass. So for the sun, it is 1. For the Earth, it is very small, okay, of about 10 to minus 6. For a white dwarf, it is about solar mass, so it's close to 1. For a neutron star, we'll see in a few slides that we don't really know what is mass of neutron stars, but it's not going through a large interval, so it's between 1 to 2.5, 3 solar mass. So we don't really know what is the upper limit. So I put something like 3. So 3 is certainly a good estimate of the upper limit, but it may be slightly below. We don't really know yet. Okay, and for a black hole, so it goes. So we expect that there is a gap in the mass, and so after the upper limit of a neutron star, you can create a black hole. So these two limits are connected, and you can have some supramassive black holes like the one in the center of the galaxy. Okay, so you have also, there's a radii in units of sun radius. Okay, so for the Earth, And for the white dwarf, it is also a small value. It's a small fraction. But for a neutron star, which is even more compact, it's even smaller. So it's about 10, 12, 13 kilometers. And for black hole, it is not a quantity which is very well defined. So we'll take the Schwarzschild radius as an estimate of a scale for a black hole. And this Schwarzschild radius is 2 times J times the mass of the star divided by c square. So for instance, for a system which has a mass of the sun, so the Schwarzschild radius, okay. So let me call it like that. So the Schwarzschild radius associated to the solar mass is of the order of 3 kilometers. Okay. So you see a neutron star with 12 kilometers radius has a radius which is only 4 times larger than the Schwarzschild radius. So it's not a black hole, definitely, but it's not very far from a black hole. Okay, and you could also define. Now I have to. So you could also define what is called the relativistic parameter, which tells you about your proximity to the Schwarzschild radius. Okay, so this is the ratio of the Schwarzschild radius divided by the actual radius of the star. So for the stars which are not ruled by general relativity, we expect that this ratio is very small. And indeed, for the sun, for the Earth, and for the white dwarf, you see that this ratio is extremely small. But for neutron stars, you see that it is not very far from 1, okay? 0.1, 0.2, maybe larger, so it depends on the mass of neutron star. But this explains why if we want to describe neutron stars, we need to solve the general relativistic equations. Okay, everything clear? Okay, so this was somehow an introduction of why now we go for more complexity, and we address the question of general relativity. So the Einstein equations can be written in this way. So you have the Einstein tensor J mu nu, and you have the impulsion tensor T mu nu. Okay, and in between you have this constant, and the Einstein equation relate the J mu nu to the energy tensor, energy impulsion tensor. So in a way, how to interpret these Einstein equations is on the left-hand side. So yes, left for you as well. You have you have a description of the time space. Okay, so if you have a space which is curved, for instance, so this is given by this J mu nu, okay, which can be developed like that. So I will not enter too much into the details of the different components because I don't have much time. So on the left-hand side, this of this equation, I mean, this equation describes how space is deformed, and on the right-hand side, you have an information about what is the energy that you put in this in your space, and in a way, if you read it from right to left, okay, so you interpret it as you deposit some energy in matter, and as a consequence, that generates a curved space. Okay, and if you read it from left to right this time, so it tells you for a given a deformed space-time what is the energy which is associated. So it's a way to establish a communication between space-time and energy. Okay, and this is how we interpret this Einstein equation. So the matter tells space how to curve, and the space tells matter how to move. Okay, and this is a simple picture where in general relativity you replace the force by a deformation of space and time. Okay, so just to make a link between these equations, so there are not simple equations to solve, so there are 10 nonlinear equations to solve. Okay, and to contrast that with what you do in the Newtonian limit, you have only one equation. Okay, and in addition, this equation is linear. Yes. Yeah. Yeah. Exactly. Yeah. 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 To my knowledge, I mean, this is it's not a question that people address. Do you have any more information than me, or? Yep.
I guess someone has done calculation, but usually
Mhm. Yeah. But this is a good question, and so in a way, yes. Yeah, I mean, if you do some general relativity numerical simulations of, let's say, for instance, you shake the star and you see how it reacts to any shaking, or you do binary neutron star merger, so then it is in a strong field. Then yeah, you have some viscosity that you put in the system. At least you have to add some kind of numerical viscosity, otherwise you have some densities which move, or you have some shocks, and it's numerically difficult to solve. Usually, this numerical viscosity that you put is way larger than the actual viscosity of matter. So maybe this is the reason why it is not added, because there is this numerical trick which does not really require the introduction of a microscopic viscosity. But I'm not really an expert on that, so yeah. Okay. Okay, so yes. Mm-hmm. Yep. Yep.
But I heard that there are a lot of works which want to get improvements or modifications of this general.
Yep.
So I didn't understand why
to improve the general relativity?
Yes.
Well, I mean, there a need I don't know, but there is a will of researchers to determine whether general relativity is enough, or whether one requires more advanced theory, because in the way that you obtain the Einstein equation, you use a principle of simplicity. So what you assume is that you write the most simple equations, but it doesn't implies that the equation have to be simple. Maybe reality is more complex than what you do. So at least people try to extend general relativity by adding some more complexity. So by going beyond this simplicity principle. But up to now, I mean, general relativity is still extremely correct and very well in agreement with all what we know. But it doesn't mean that tomorrow we may have an observable which will tell us that general relativity is wrong and we have to do something more complex. Okay. No more question? Okay. How to solve the general relativistic equations? The way to solve it is to determine the metric which drives your system. Okay, so what is a metric? So for instance, here, this is the most general form, okay, of a metric, which respects the symmetry, so the spherical symmetry. So your metric, it is a measurement of in space time. Okay, so that I think you have all got lectures on that. So you have you have a term which tells you about the time in your frame. Okay, and you remember that in special relativity, the time is a function of your speed or of the differential speed between two frames. And you have the coordinate, space coordinate, okay? And you know that in general relativity, at variance with Newtonian physics, space is not an absolute frame, okay? So you cannot say anymore, you cannot distinguish or separate time and space. So what is in absolute frame is space-time, okay? And that matrix here, which is written here, it is the thing which is transformed. So this is a quantity which associates time and space, and which is conserved. Excuse me, not transformed, but conserved. But for instance, in special relativity, you know that if you have a bar, okay, and you are in the frame of the bar, then you can measure length. But if the bar is moving and you are in this frame and the bar is just moving, you know that you have a compression of the length in your frame. But for someone who is moving together with the bar, he doesn't see anything. Okay, so there is a conservation not in space, but there is a conservation in space and time. And this is what is described by this matrix. So if we are in vacuum, so there is no energy, so we are in. So the equation to solve is this J mu nu or R mu nu equals 0. And I will not do the demonstration, but what you can show in this case, it's not very complicated, it's just a bit lengthy, is that the coordinate J00, so maybe, so this is J00 square, and this is here J11 square. No, why, excuse me, made a mistake, there is no square. given simply by these equations, okay, for J00 and J11. Okay, so so the two quantities which are the mu and the lambda, which are there, are fully determined. So this is, for instance, the metric that you would use if you are out of a star, okay, and you want to describe the space not in the volume of a star, but in the external part of the star. Okay, so as soon as you enter into the star, then you should change the matrix. And this is, yeah, let me skip it a little bit. Okay, so this is what we, this is a reason why when we enter into the star, we have to recalculate a new matrix. And again, we start with this general form, but now we don't have J mu nu equals 0, but we have to solve, assuming this the symmetry, the spherical symmetry, we have to solve the ancient equations. Okay, and again, I don't want to do this long derivation. It's a bit boring and not very difficult. There are books where you can find them, but what you obtain from this derivation, it is a set of equations, okay, for lambda and for nu, okay, which are the two quantities that determine this matrix, and by solving the general relativity equation, you obtain these two equations, okay, where you see that you have included mass. And this time I made no mistake, so it is a rho. So the included mass is defined like that. Okay. And you have this differential equation to determine what is the value of nu. So you need the boundary condition, and the boundary condition is one at the radius of the star. So you want your metric to be continuous. So at the radius, you want to connect to the Schwarzschild radius, to the Schwarzschild metric in empty space, in vacuum, and therefore you impose this condition. Okay, so if you do that, then you obtain at the end of the day these two equations, which replace the Newtonian equations that we have presented before. So the first one is not very different. It is an equation that describes the included mass. And the second one is a bit more complex, okay, but it is also an equation that tells you how the gradient, how the pressure evolves from the center of the star towards the external part. Yeah, and let me just do a simple exercise. So we start, for instance, from this equation, okay, which looks very ugly, but let me factorize some terms. Okay, so so I have this factor, which is there, but then I want to factorize this term. I want to factorize this term, and I will also factorize this term. Okay, so if I factor these terms, then I have a factor which is minus j over rc squared. This is my first guy. Then I have rho c squared. So this is energy density. Then I have mc squared. Then I have also, yes, so I have also to divide by rc squared. And then what I have 1 plus P divided by rho C square. Then I have 1 plus 4 pi R3 P divided by MC square. And I have 1 minus 2 JM over RC square. Okay, and I remind you that the Schwarzschild radius is 2JM, excuse me, over C square. So this denominator is simply 1 minus the Schwarzschild radius divided. Excuse me. Yes. No. For the, yes, this is why I put a small m. Or, yeah, maybe I should call it a small Schwarzschild radius. Okay, and then it is the small Schwarzschild radius. And of course, if I take small r equals the radius of the star, then I recover this quantity. Okay, so and then what you see, okay, so you have C to the 4, C to the 4, okay, and then my dp over dr is minus j m rho over r square 1 plus something 1 plus something divided by 1 minus, so this pole, okay? And if you remember correctly, this minus jm rho over r is the Newtonian limit. So in this expression, what I have what you can see is all the 1 are due to the Newtonian limit, and you have corrections, and these corrections translates the effect of general relativity. Okay, so if you take the limit, so now it's a bit charged, but if you take the limit of the sound speed going to infinite, then you recover Newtonian limit. Okay, so a way to so it is in this form. You see very simply that you can continuously go from general relativity to the Newtonian limit just by increasing tremendously the light speed. But we are therefore we are faced with the same problem as the one in Newtonian physics, which is that we need an additional equation to close the system because we don't have enough equations to determine all the variables that we want, and this is the equation of state. So what we need in order to resolve the hydrostatic equilibrium of neutron stars is to add to the TOV equations the equation of state. So the relation between the pressure and the density. Okay, and and let me just write here something that is new compared to before, which is that in fact what now I call rho is not only the mass density, okay, which you were saying before. Okay, so this term, okay, mc squared times m is the mass density. Okay, the rest mass. Yes, yes, the rest mass density. Yes, exactly. But now you know that mass and energy are similar quantities, and in general relativity, what we call as a density does not include only the rest mass contribution, but also the internal energy. Okay, and this is what I'm writing here. So an energy density. So remember that the Greek letters I use are for something density divided by the volume. So the energy density is defined as rho c square. Okay, and the energy density has a contribution from the rest mass. So the particle density n times the mass. So if we suppose that we have a single particle fluid, so it is just the mass of this fluid. So that first term is the rest mass density. And we have a contribution from the internal energy. And the internal energy, just to have an idea, it is, for instance, what in the free Fermi gas that we discussed in the first lecture, it is just the kinetic energy. Okay, so the kinetic energy of a particle is an internal energy. But you can also have, and you do in general have also an effect of the interaction. And so the kinetic energy and the interaction, so all these energies are into the internal energy. So again, yes, yeah. Yep. Yes, you're right. Okay. Yeah, yeah, exactly. Yes, this is a mass of, yes, exactly. Yep. Yep. Yeah, yeah. You're right. You're perfectly right. So this is a mass of a nucleon, for instance.
If you consider just nuclear mass.
Yep.
But in principle, this is the average between the mass of the components.
Yep. 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 Yeah, yeah. If you have more than a single fluid, you have to sum the mass of the different and the density. Okay, so so for instance, if you describe matter with nucleons and hyperons, okay, so the energy density, so or the rest mass contribution will be the density of nucleons times the mass of the nucleons, plus if you have only lambda, for instance, it will be the density of lambda times the mass of the lambda particle. And if you have additional terms, then you have to add the contribution of all these additional particles with their associated density. Yeah, but yeah. So if you want to be exact, you have to add the. But okay, you know that it is negligible. But if you have muons, okay. So you have to add in the rest mass all the contribution from all the particles in your medium. Yes, that's correct. But what I wanted to extract, to show from this last equation is now if I write the density rho, okay, then I have to divide by c square. Okay, so this is n times mn, okay, plus n times internal energy divided by c square. Okay, and again, you see that if you take the limit of C going to infinite, you recover what you would introduce as a density in the Newtonian limit, which is just the contribution of the rest mass. Okay, I'm not going as fast as I want, but it is not very important. Okay, so this is in a way what I said before. Okay, so on the left-hand side you have general relativity. On the right-hand side you have the equations. I have just rewritten there the equation for Newtonian physics, and you can go from the general relativity and you can recover the Newtonian equations if you take the limit of the light speed to go to infinity. Okay. And this afternoon, for instance, you will have a solver that solves the general relativity equations, but the same solver will also solve the Newtonian equations. Okay, and you will be able, for instance, to compare, if you consider the left-hand side. So for a neutron star, you will be able to say, well, what if I neglect totally the general relativity corrections and I solve the equations that I would have solved, assuming it is Newtonian, and you will be able to see the difference between the two. Okay, so so these are just some examples on. So you will produce. So this afternoon, in fact, with a Python toolkit, you will produce such graph. Okay, so this graph shows you, for instance, as a function of the radial coordinate in the star, you will be able to determine what is the enclosed mass. Okay, where here at the radius you have the total mass of the star. You will be able also to generate the pressure profile for a given equational state. So how the pressure evolves as a function of the coordinates, and you will be able also to determine the evolution of the density inside the star. So that is thing that you will be able to do. And here, what I compare, so I have taken 4 equational states, and you can see the differences. So all these stars have the same mass. Okay, 1.4 solar mass. This is what I have fixed. You can see it here. Okay, that the limit, the mass of all these systems are different, but because you have different equational states, you predict that for same mass, the different system will have different radii. Okay, so in a way, this confirms what we were saying at the beginning, that measuring the radius will allow you to select some equational state. So the radius translates the effect of the equational state. So if you have a mass and radius of a neutron star, for instance, you will very accurately be able to determine among these 4 equational states which one, for instance, is the physical one, is a real one. And you see also that because there are different equational states, you have different pressure or different density profiles inside the star, and it is unless someone goes inside a neutron star and look what is inside, it is pretty difficult to determine which of these equational states are good, just based on the pressure or density profile. But what you can do is, as I said, measuring the mass and the radius, you can filter out the equational state that do not reproduce the observational data. Okay. So what is the program we have? So we are all interested in describing the dense matter, and so the property of extreme matter, and this is what we call the equational state. So this is what we have on the left-hand side, and here, for instance, in this figure, you have different kind of equational states. So either strange core, or you suppose nucleonic matter, or you suppose quark stars. And you can generate different equational state. You include that into your TOV solver, and you will generate, by changing the pressure inside the star, you will generate a set of mass and radii, okay, like that. And if you look at the colors, you will see that okay, if you have a set of points, for instance, that goes like that, of observational points, then you will be able to say, well, this is a nucleonic model which is compatible with observations. Or if you have a set of mass and radii which goes like that, you will say, oh, the nucleonic model not correct, but it is more a quark star. Okay, so the program is, the scientific program is to improve the detection, the measurement of mass and radii of neutron stars, in order for us to determine the composition and the equational state of dense matter. Okay, then I have, I don't remember at which time I should stop, or no, I mean, unless you are tired, but. Okay, good, okay, very good, okay. So, okay, so just to make the point, or to summarize, so this afternoon, you will have a code that will allow you to generate as many curves as you want of this way, of this type. But then it is not the end. I mean, it is not, you cannot do only that. You can go a little bit further. And now we will also together analyze these solutions of the TOV equations. So the first question is, you obtain a star, but is the configuration you obtain is stable? Yes. This one? Excuse me. Can you? Okay. So this quark stars, okay, this one. Yep. Okay, so this is a quark star. I'm not the author of this paper, but I think this is a quark star without a crust. So it's yeah, yeah. I mean,
The point is that that is so the density at the surface of the star, where the pressure is zero, so the order of Newton matter when you do times.
Mhm.
As a consequence, mass density. This is not true for normal. This is not
Mhm. Yep. How do you find? Yep. But yeah, but maybe what you mentioned is about the internal pressure. So you have to make a distinction between the pressure, internal pressure, the one that you obtain either by assuming you have quark matter, self-bound quark matter, so that defines the pressure. And so this is internal pressure, or in a way, the resistance to gravity. And the final pressure in a neutron star, which drops to zero at the radius. And this is not internal pressure, it is a global pressure. Okay. So yes, so the first question is whether the equations that or the solution that you obtain is a stable solution. And so I will discuss about necessary condition. It's not enough, but at least it is a prerequisite that that tells you whether your system is stable. So suppose so this is a mass as a function of the pressure, okay, as a central pressure. So the parameters that you fix in order to determine the solution. And so at the beginning, you have curves that goes up, for instance, and let's analyze what occurs if these solutions, when the mass increase as a central pressure increase, are associated to stable solutions or not. Okay, so we start from a configuration that I call A, which lies on top of one of the equational states. So let's take, so this is a blue, for instance. Okay, and so I am on a stable solution. And now I want to know if this solution is, excuse me, I am on a solution, the blue solution, and I want to know whether this solution is stable or not. So what I do is that I will shake, I will perturb my solution, and I want to know whether I have a restoring force that brings me back to my initial stability condition, stability solution, or whether I will escape and move far from it. And this is a way to say or to determine whether I am at equilibrium or not. If my solution is an equilibrium solution, if it is a minimum solution, so and not a maximum solution. So suppose, for instance, that I'm able to compress my star and to increase the pressure. So I go from A, from the point A, which is there, towards a point B. Okay, maybe it's better if I zoom in. Yeah, it's not, so B is not on the red curve. It's just a fictitious non-equilibrium solution, so that I obtain. And it is not on equilibrium because, I mean, for the equational state I consider, because B is not on the blue curve, okay? And the blue curve are all equilibrium solutions. Now, yes, so this is my pressure. So I'm in this out of equilibrium solution, B, okay, associated to a given pressure. So where is my equilibrium? Okay, so what is the equilibrium configuration associated to this pressure? So what I do is that I figure out what is this pressure inside my system, and I go up, and you see I go to point C, which is the equilibrium configuration associated to the pressure of my point B, which is a perturbed star originated from point A. And what you see that at your at C, you have a mass which is larger than A. Okay, so and you cannot create mass. So what the system will do is that it cannot go to C. So since it cannot go to C, then if you perturb, you go to B. If you were able to jump to C, it would jump to C because it is an equilibrium solution, but it cannot because the mass is larger, and therefore what it will do is that it will go back to A. Okay, so in this way, you see that when my mass increases as a function of the pressure, I am in a stable configuration. Now assume that now I'm there. Okay, so I am in the region where my mass decreases as a function of the internal pressure. Okay, so again, I do the same. So I go from A to B. In B, I have a larger pressure. I look what is the stable configuration for the same pressure, which is in B. And then I'm in C, and you see that in C, now the mass is smaller. So you can access to this system. And therefore, if you are in this configuration, so you will go from A to B. B is out of equilibrium, but he can restore the equilibrium by going to C, and therefore it will go to C. And for this reason, you go from A to C. And if you go from A to C, then you depart from your equilibrium solution. So when you are in this branch which is going down, you are in an unstable configuration. And what makes the difference between, yes? The Byron number? Ah. That's year. Okay, I have not put this number. Yeah, I should. Yeah.
The point is that when you get tension, it's a rather so you have the prejudice of the fundamental law. What happens is that the structure branch.
Yep.
The decreasing branch is fundamental of square is
Yep. Yep. But yep. Yeah, I wanted to simplify a little bit, yeah, and not enter too much into, and especially because this is just a necessary condition, and you can, I mean, the question of the stability of stars is a very important question, and it can be more complex than just this simple picture. Yeah. But then, yes. Yep. Well, you may. I mean, it is possible. So, for instance, you may expulse it or you may eject it from your system. You cannot increase the mass because you don't know where it will come, but you can decrease the mass. Yeah, or just you can a part of the mass of the system could be ejected, for instance. But okay, this is a very simple heuristic demonstration, and it can be made in, I mean, more complex. But I mean, the simple thing I wanted to show, or which that it illustrates, is that you have two branch, which is a stable branch that we discussed at the beginning. So this branch here, and the unstable branch here. And what makes the difference between these two branches is what we call the maximum mass. Okay, so these points A, B, C, they are there, here. And what they do is that they localize for a given equation of state what is the maximum mass of the system, and what is the maximum density associated to the system. And this is also something that we will calculate this afternoon for a given equation of state, what is the maximum mass. But you see clearly that in order to get the maximum mass, so you have to select a set of internal pressure, okay, not only in the stable branch, but also in the unstable branch, if you want to localize where is the maximum mass. Because, for instance, if you select only a few points here, 4 points in the stable branch, and you ask what is the maximum mass, you will obtain this mass, okay? And the mass here is different from the mass here, okay? So the first exercise this afternoon will be to generate a mesh of central pressure that includes both the stable branch and the stable and unstable branch, in order to determine what is the maximum mass of your system. Okay, so you need to explore this region there in order to determine what is the maximum mass. Otherwise, you just measure what is the mass of your most compact star. Okay, now there are also interesting features associated to neutron stars, which is the difference between the radius that you obtain and the radius that an observer will see if he is out of the star. So this is the what is called the apparent radius. So this radius at infinite for an observer which is far from the neutron star, and it is different from the radius that you obtain by solving the TOV equations. And then you have this relation between the two, which is due to and you can see that there is a correction which is there, and this correction is what we'll see later on related to the redshift. So you have your radius. You observe your apparent radius is redshifted compared to the solution of your TOV equations. And you can also define interesting quantity, which is called the compactness of the star. So it is proportional to the mass over the radius, okay, of your system. And then if you inject this compactness into this equation, you will see that the apparent radius of the star will be shifted by a function which is a function of the compactness of the star. So the compactness of the star will modify the radius of your system. Okay, so we spoke about masses of pulsars, and what I show you here is a compilation from Jim Latimer about a set of stars. So we know something like 3,000 neutron stars in the galaxy, but it is very difficult to determine the mass of a neutron star, especially if it is alone, if it is in a single configuration. But if it is in a binary configuration, then it is easier. And in fact, it is mostly in binary configurations that the masses of pulsars are observed, and this different. So in this representation, you have different colors, okay, and these different colors are related, you see, to what is a companion of the star. So you may have, for instance, a double neutron star binary system, or you may have a neutron star with a white dwarf, or you may have a neutron star with a main sequence star. Okay, and depending on what is the binary, the companion of your neutron star, you will you could solve, for instance, the Kepler relations in order to determine the mass of your system. And this is how it is done. And for instance, if you have two neutron stars, so we know maybe about 10 of them, then you can determine very accurately, okay, it is given there, the mass of this system. If it is a white dwarf, you can also determine the mass, but you see that the error bars are larger. And if it is a main sequence, you also see that the error bars are larger. However, what is important from this figure is to see that the distribution of mass are not spanning over a large numbers, and you can even determine the centroid of your distribution, and you get what we call the canonical mass. So this is somehow the centroid of the distribution of the mass of neutron stars. Okay, but it is a centroid, so you have stars with larger mass and stars with lower mass. And up to now, so the lightest neutron star which have been detected, measured, has a mass of about 1.17 solar mass. Okay, so it's pretty small, and it's not very easy to understand how one could generate such a light neutron star. So this is on one extreme. So here, for instance, you have the distribution of masses as a function. Yeah, the distribution, the number of neutron stars which are observed in by binning of masses, and you can also look what are the largest neutron stars observed. So there are a few of them, but they are extremely important and extremely instructive because they probe the upper boundary of stable baryonic matter. Okay, but from this observation, you say, oh, I have observed a mass with 2 solar mass. So you know that the upper boundary is above. So your observation determines the lower boundary of the maximum mass. Okay, you don't know from your observation. You have an event or a counterexample which tells you that the mass cannot be below, but it can be any number above. So what you determine from your observation is not the maximum mass. It is a lower bound of the maximum mass. Okay, so all these numbers that I give here are just observations of neutron stars, and you know, therefore, that if you have an equation of state, you should reach, for instance, at least 1.9 solar mass to be compatible with this observation, with this data. Or if you want to be compatible with this data, you have your equation of state should reach at least 2 solar mass. And what I put also there is the uncertainty. Okay, so for instance, here the uncertainty is very small. So how to read it? It is 1.908 plus or minus 0.016. Okay, this is just the two last digits. But there, for instance, 4 means that it is at least twice the uncertainty of the previous measurements. So it could go up to 2.05 at 1 sigma for 1 sigma uncertainty. Okay, and for 2 sigma uncertainty, it could be up to, it could go up to 2.09, or it could go down to 1.92 at 2 sigma. Okay, so so it's not important. It is not only you should concentrate on the centroid distribution, but you should really look what is the uncertainty which is given by observers. And this is especially true, for instance, for this the most massive stars which are there. Okay, you may say, oh, someone have observed a 2.14 or a 2.27 neutron star. But if you look really the uncertainty and you say, well, it's, for instance, I will consider 2 sigma uncertainty, you see that this observation is not more accurate than this one, because if you remove twice the uncertainty, you get this one. So the uncertainty is a quantity which is also extremely important. I believe that you know it, but it is another example where you have to look not only at the centroid, but also at the uncertainty associated to a measurement. Okay, so I continue. So before what we were, okay, so what I was discussing was the maximum mass, was the mass of the system. Okay, so you take the enclosed mass for given coordinate, and then you equalize this coordinate to the radius that you determine, and that fix the mass of the star. Okay. Then again, let me see. Again, you can write the density as the rest mass density plus the contribution coming from the internal energy. Okay, and so let me see. Okay, so yes, so you remember, okay, this relation. So an energy density epsilon, okay, is equal to a mass density c square, and rho is decomposed in terms of rho zero, which is the rest mass. Okay, so this is rho zero. The rest mass density, c square, plus the internal energy divided by c square times c square. And if you remember also, epsilon zero is the particle density times, if you have only nucleons, mnc square plus the internal energy. So now I use Latin letters, which means that it is energy per particle. Okay, so if I now equalize these two things, then I can say that rho zero, the rest mass density, is n, the particle density times mn. Okay, and the other thing is pretty simple. So the energy density is n times the internal energy per particle. Okay. Yeah, maybe I should insist again. I didn't comment it too much about it before, but so this is this what I have written there. So my unit volume in general relativity is not the unit volume that you are used to in Newtonian physics. You have also, so it is not only 4 pi r square dr, but you have also this correction, which is a general relativistic correction. Okay, so when you measure a volume, you have to consider, on top of what you would have written naturally, you have to consider this correction. So suppose that I would like to determine not the total mass, but the gravitational mass of the system. Okay, then I will have to integrate over this volume my energy density rho. Okay, so this is what I'm written here, what I have wrote here. So the gravitational mass of the system that now I call mj. Okay, it is very similar to this quantity, but instead of integrating my energy density, I also take into account this general relativity correction. And I can also say, well, what I'm interested in is not the contribution of the energy density with the internal energy, but only the rest mass. Okay, so I can say, well, what is the rest mass of my star? And therefore, I apply the same expression as here, but you see, I will take only the contribution coming from the rest mass in the energy in the energy density. So my rest mass, I can compute it by using this expression. And what is the difference between the total mass of the star and the rest mass? So so the rest mass is simply saying that I disregard the contribution coming from the internal energy, and I also consider this correction. So the difference between the two, these two masses, is the binding energy. So this is what I'm writing here. But you can also say that the difference between the gravitational mass mj and the rest mass m0, okay, originates from the internal energy, and we have seen that this internal energy is a relativistic correction. Okay, so I can say I can say that, for instance, my gravitational mass, okay, is given by my rest mass plus post-Newtonian correction that I call Pn, okay, which is therefore what I have neglected in M0. So I have to add for this correction, I have to add, for instance, 4 pi the integration of not rho 0, but the internal energy. Okay, the square root times dr. Okay, so this is so you see there is not only the total mass which is interesting to evaluate, but there are different byproduct of the mass. And let me then come to the binding energy. Okay, so what is the binding energy? So this is the energy that you gain in binding a star compared to a system where the particles which would compose your star would be apart. Okay, suppose that they are blown up and vaporized in the entire space, then you see that they don't do that. So in a way, they gain some energy. They gain some binding energy by being stick in a neutron star instead of being vaporized and distributed through the entire space. Okay, so I said that the mass is the rest mass minus the binding energy. So the binding energy, I can express it as M0 C square minus the energy, the mass of your system. Okay, and one additional thing I could add is suppose I have only nucleons in my system and I want to compute the baryon number. Okay, so what I should do if I want to compute the baryon number is I should take the particle density NB. Okay, the number of particles per unit volume, and I should integrate this quantity times my volume, and at the end I will have a number, which is a number of particles. Okay, so this is, for instance, this is how I would obtain a particle number, and this afternoon we'll do this exercise. And typically, what you expect to obtain for a neutron star is a number of particles inside a neutron star of the order of 10 to 57 particles. So inside a neutron star, you have approximately 10 to 57 particles. Okay, so now I should remind that in M0, I was in order to get M0, I was integrating my number density times the density, the mass of my particle. Okay, so I can express this as A times mn c square minus the mass of my star. Okay, so the binding energy, if you compute the number of particles, A, you multiply, if you use it can be more complex if you have not only a single particles, but hyperons and leptons, and you want to, but let's consider a very simple system. So my binding energy is A times the mass of my nucleons, C square, minus the mass of the star. And this is an interesting quantity because, so I took this figure from a paper by Shabana et al. And you may know that the last core collapse supernova which have been observed was in 1987, and the name is SN 9087A. And there were an estimate of, so they release a lot of neutrinos. And from this neutrino, one was able to estimate the energy gained by the collapse. So the energy gained by the collapse is the binding energy, can be transformed, associated to the binding energy of your system. And this quantity, so in erg, so this is CGS units. So it's it's 10 to minus 7 joules in unit in international system. So the binding energy, okay, extracted from this observation was of the order of 4 times 10 to 53 ergs. And if I report, so this is for a given equatorial state, okay, you can compute the binding energy as a function of the mass. And if you report this quantity with, and you see there are, I mean, quite large uncertainties. So this is the reason why at the end you have a big square. But if you report this measurement like that, okay, you can determine what is the mass of the system that came out, with, I mean, which is able to gain such a large amount of binding energy. And you find that neutron stars are possible. And not only they are possible, but you find that if you have a neutron star with about 1.4 solar mass, then you are compatible with your observation. So in a way, it is an indirect confirmation that in the collapse of massive stars, you form a central object with a binding energy which is of the order of the energy which is released by the collapse. And such a large amount of binding energy is compatible with a 1.4 neutron star in the center. Yeah, I can stop here. Yep. Yeah. Yep. Yes. Yes, this is why I put a minus. Yeah. Yeah, it's positive or negative. It always depends who is watching what. Okay, so what I have done. Let me see.